So good evening. We are now into the week 3 of the live interactive session for the course IC Engine and Gas Turbine. My name is Abhishek and I'm a PMRF research scholar at IIT Guwahati. And these are my YouTube link where you can find the recorded lectures for the current week and for the past weeks. And I am from Department of Mechanical Engineering, IIT Guwahati. So we'll start with summary of the lectures that were covered this week. So basically, what we were seeing was different type of cycles, IC engine cycles that were possible. We have already covered Otto cycle and diesel cycle, and if you see that one of the things that has been arising is that what is the difference between a thermodynamic cycle and a mechanical cycle. So last class I have told that a mechanical cycle is any general cycle where certain processes are taking place and the states are being repeated one after the other. For example, we'll go from 1 to 2, after that from 2 to 3, from 3 to 4, and back to from 4 to 1. So this can be four processes consisting of a cycle. In a cycle there will be four processes, and this is what is a mechanical cycle. But a major difference between a thermodynamic cycle and a mechanical cycle is that in thermodynamic cycle the initial contents or the initial contents or constituent should be same as the final contents or the constituent. This should be the thing. But if you see in general, when there is any combustion, first we put, let us say we use hydrocarbons. So let us say it is some hydrocarbon CXHY, and we'll be giving that hydrocarbon with certain amount of air. Now when this will be combusted, if there is a complete combustion, then there will be presence of CO2 and H2O. But if there is incomplete combustion, we'll be encountering a presence of carbon monoxide, and some part of might be hydrogen, and some if there is a rich mixture, then we'll be finding oxygen. So the content and the constituent has already changed. So that is why we cannot take it as mechanical cycle. And if we are not taking mechanical cycle, then how do we analyze? Because we have to analyze what is the efficiency, what is the work output. And if we don't know what is the cycle, what are the processes that are being taking place, then we cannot analyze. That is why what we do is we assume that this is the certain process is mapped to a thermodynamic process. And that is why what we do is we try to each and every process is mapped to a in ideal condition what might be the case. So let us say, if you see from 1 to 2, there was compression. We don't know that whether this compression is isentropic or it might be polytropic. We generally take PV to the power gamma is equal to constant. Now this we can only assume that it is isentropic when we take the consideration of thermodynamic cycle. That is why we assume the mechanical cycle to be equal to a thermodynamic cycle, and we do our analysis based on that. So now if we go this, what is this cycle? If you can answer me. Seeing the cycle, what is this cycle? Where the volume where the heat addition is done in constant volume. What is this cycle called? Can you reply?
Auto cycle, sir.
This is Otto cycle. And this is diesel cycle, where the heat addition is done in constant pressure process. This is the basic difference between Otto cycle and diesel cycle, and we have already covered. This is the valve timing diagram. If you see, there is this is where the spark ignition starts, where it starts, but we'll be having some inertia, so it will take some time. But in ideal case, we assume that the combustion has started here and it has been completed here, and it takes place at constant volume. But in real case, this is not so. And if you see in the constant pressure process, what is done here is that the pressure is kept constant. But in real case, is it possible to keep the pressure constant during a combustion process? It's not that easy. So what we do is, how do we map this heat addition processes in both the cycle? This I've already said in the last class. So generally what happens is that whenever there is let us say there is an engine, and let us say the piston is here, it has reached the TDC. So at this location, in an idle Otto cycle, there is spark. There is spark, and we assume that at this particular instant the fuel has combusted, and thus we assume that means the piston has not moved down during its power stroke, that is in its expansion stroke. That is why we assume that the volume is constant in an Otto cycle. But when we take place of in diesel cycle, we assume that the spray, that the fuel is sprayed after compression. It will take some time for the fuel to mix with the air and get combusted. During this process, the piston has moved a certain distance. Piston has moved certain distance from the top dead center to the bottom dead center, and that is why the volume has increased. And we assume that this much amount of volume that has increased is and the heat has been added. It is done so that pressure can be kept constant. As the volume has changed, volume is directly proportional to the temperature. So the temperature will there will be combustion, and that this has been, and we think that there is a certain amount of temperature that has increased, has led to the increase of the volume, and this is what is called the cutoff ratio. This one we denote by beta, and this one we have already covered in last class. But this process is not at all possible in actual condition. That is why what we do do in our modern cycle, we actually split the combustion total combustion from 2 to 3 to 4 into two cycles, into two processes. This is number one process, this is number two. In number one, what we do is there is combustion in constant volume, and then the combustion or the heat addition is taking place at constant pressure, and this we can call it as dual cycle. This we generally use in high speed modern engine. And what is generally is done that earlier only one process was used, whether it is we are keeping volume constant or whether we are keeping the pressure constant. Now what we are doing is we are splitting the whole pressure whole combustion into two parts. First one will be at the constant volume heat addition, and then it will be the constant pressure. So the rest, all the processes that are taking place in this thermodynamic cycle is same. That is what I mentioned here. 0 to 1 is the pressure intake, constant pressure intake. The fuel or the air will be sucked in this cycle from 0 to 1. After that, from 1 to 2, there will be isentropic compression, where we increase the temperature and the pressure. And then what we do is there is a heat addition of the constant volume. There is the combustion is taking place from 2 to 3. And after that, from 3 to 4, there is constant pressure heat addition. So there will be two processes where we are splitting the whole heat addition process into two processes, 2 to 3 and 3 to 4. And then there will be isentropic expansion from 4 to 5, where we'll get power. This is the power stroke. And from 5 to 1 is the constant volume heat rejection, or what we know it is also called as blow down. And the final is the constant pressure exhaust. This one we have already covered. So when we plot, this is the T versus TS diagram, and we can see that what we have just if you see from 1 to 2, 1 to 2 is the isentropic process, isentropic compression process. So the S is constant. After 2 to 3, this is the constant volume heat addition. So it will be a curve, and this is constant volume heat addition. This is isentropic process. The entropy is constant. Delta S is equal to 0. Here pressure is constant. And one of the things that I think you might be knowing from your basic thermodynamics, that what is the slope of a constant volume in a TS plot of a constant volume curve? What is dt by ds of a constant volume curve? Do you know the what is the value? Anybody? It is T by CV, and here it is T by Cp. So based on these two, let us say the temperature is constant, temperature is same, Cv is greater or Cp is greater in an ideal gas.
CP.
Sorry,
CP, sir.
Cp is greater. So the slope of this will be, although here it might not be visible properly, but this slope, you can find that the slope, let us say this is θ1 and this is θ2. So θ1 will be greater than θ2. This is the way through by which we draw a TS plot. Then 4 to 5 is the isentropic expansion. This is where S is constant, and here again constant pressure, heat rejection. So this is the all about the dual cycle, and then we'll go move to the next summary of the next lecture. So in lecture 9, there we have started some portion of carburetor, but majorly there were two major things that was covered is when we compare the cycles. So now we have already covered, there are three cycles that we have already covered. One is Otto, one is dual, and one is diesel. Okay, so we'll compare which cycle is better in which case. So there are particularly two cases that we have considered. One is when there is constant pressure ratio. So RC is constant. So in this case, what happens is, so truly speaking, what is happening is that when we are plotting any diagram on a PV plane, or let us say in XY plane, we always need two conditions. You will only say that X is equal to this much. I cannot plot that figure because you have to tell me what is Y, or you have to give me the function of that. So here also, if I only say it's constant pressure compression ratio, it is incomplete. But still, why we only consider we only write that it is a constant compression ratio, that I will be telling you. So what is done is constant compression ratio. That means what will be happening is V1 by V2 will be same for all. V1 by V2 will be constant. So if you see, what I have marked is 1, 2, 3, 4. This is Otto and back to 1 is Otto cycle. This is Otto cycle. 1, 2, then back to 2, then we'll go to 3 dash. Then this point I have not marked. Let us say this is some X. This is X. Then 4. Then back to 1 is dual cycle, because there are two portions of heat addition. One is constant volume, then is constant pressure. Then the final 1, 2, 3, 3 double dash, 4, and back to 1 is diesel cycle. This is diesel cycle. Okay, so if you see in this case, and this is its TS plot. TS plot also, if you see 1 to 2 is same for all. We know that there is a constant compression ratio, so 1 to 2 will be same for all, but the heat addition process will be different for everyone. So 2 to 3 is the constant volume. This is volume. Black one is constant volume. Red one is split into 2. This is constant volume. This is constant pressure. And this one is diesel cycle, which is constant pressure. Rest all everything is same. Now based on this, this is our compression, this is our efficiency. Efficiency is 1 minus Q rejected by Q supplied. So can you tell me whose efficiency will be higher in this case? When the pressure is constant, there is a compression ratio is constant, whose efficiency will be higher and why? Is anybody listening? Yeah, so you can answer. Is my voice
No,
audible,
sir.
right?
Yes, sir.
Okay. So I will explain why, in which case the efficiency will be higher. So let us say we'll compare based on the Q rejected, Q rejected and Q supplied. For that, in which plot we get to know work. If we want to see, we want to calculate the work done. So in PV diagram, how do we find the work done? This one you might be knowing. In PV diagram, how do we know work done? It is the area under the curve. Do you know this? Someone please respond. Do you know this? The area under the curve on
No, sir.
volume axis. This is how we calculate the work done in a PV diagram. But when it comes to PS diagram, how do we calculate the heat? The area, area inside the area under the curve. Area under the curve in on entropy axis. Okay, so if you see this particular case that I have drawn is the constant compression ratio plus the heat rejection is also constant. Okay, so if you see the when is the heat addition is taking place, in which process the heat addition is taking place, from 2 to 3 or let us say from 2 to 3 dash or 3 double dash, correct? This is X. So the if you see the heat addition process for auto cycle, let us say I am drawing the heat supplied in auto cycle. Sorry about the lines. Okay, just I will. So this is the area under the curve for the auto cycle. But when it comes to diesel cycle, the area under the curve is from here. Okay, so everyone understood that Q supplied is the area under the curve on the entropy axis. Whose Q supplied is more? Whose Q supply is more for whom? Auto cycle or diesel cycle? Tell me.
Auto cycle, sir.
Correct. So the Q supplied for auto cycle and diesel cycle, if you compare, then Q supply for auto cycle is higher. But if you compare the Q rejected, just tell me Q rejected for auto cycle, whose is higher or whose is less? Rejection, heat rejection is taking from 4 to 1. So just tell me who's 4 to 1. So it is same for both the auto cycle and diesel cycle, correct?
Yes, sir.
So,
Yes, sir.
so Q rejected for auto and diesel both are same. So whose efficiency will be higher? QS.
Auto cycle.
Yeah, because QS is higher, so this ratio will be lesser. So efficiency will be higher. So, auto cycles efficiency is higher when the, compression ratio is constant. This is diesel. This is dual. So dual is in between both. As I said, this is a type of hybrid. So it will always stay in the performance is always between the Otto and the diesel cycle. Okay. And whenever see there can be any condition. So there will be like constant compression ratio and heat addition. Heat addition is constant in both, and compression ratio is constant. If you see that compression ratio is constant, that means always Otto cycle efficiency will be higher. In any case, the second case, no need to see, will always be that the Otto cycle's efficiency will be higher than the diesel cycle. Then the next case we'll see, it is the same peak pressure. So peak pressure, if you see in a Otto cycle, when does the peak pressure is achieved? The same marking I have done, 1, 2, 3, 4, 1 is the Otto cycle, that is marked in black. The blue lines is for diesel cycle, and for the red lines are for the dual cycle. So you tell me in where is the highest temperature achieved in all the cycle? Highest temperature or highest pressure when it is achieved?
3.
3, correct. So 3 is the process. 3 is the state point where the temperature is highest. Temperature is highest, and pressure is also highest for all the cases. But to reach 3, what you can see is that Otto cycle has to go through 2 different cycles, from 1 to 2, to different process, to be exact, 2 different process, from 1 to 2, then from 2 to 3. Okay, but a diesel cycle is reaching that same process in its compression stroke, from 1 to 2 double dash. It is reaching in that same, in the one cycle. So here if you compare the Q rejected and QS, whose QS will be higher in this case? Q supplied will be higher in which case?
Diesel.
Yeah. So diesel, Q supplied will be higher. You can see from this curve that the area under the curve from 2 double dash to 3 is higher than 2 to 3. So that is why Q supplied is higher, and hence Q rejected is same in both. If you see the Q rejection is taken from 4 to 1, so it is same for both. So that is why efficiency of diesel, when the peak pressure is constant, is higher. Then comes dual, then comes Otto. So these are the particular 2 types of comparisons of the cycles. Whenever the compression ratio is constant, it will always be happening that the Otto cycle will be higher, efficiency will be higher. And whenever other than that, in any case, if the compression ratio is not constant, diesel will be higher efficiency. Okay. So next we'll move to the next lecture, lecture 10. So carburation was already started in the in lecture 9, but I have included here in 10, just to summarize properly. So in what is carburation? It is a process in which we prepare the combustible fuel air mixture. So we have already covered in the first lecture that carburetor is only present in which engine? Diesel engine or petrol? Yeah, it is in petrol engine or Otto cycle. Carburetor is only present in petrol engine or the SI engine. Okay. So we in SI engine, I've already said that there will be providing fuel plus air. Will be providing fuel plus air to the cylinder. So the process of preparation of this mixture is known as carburation, because there will be different loads. If you see, there will be different loads during the cycle. Let us say it will be when the load is higher, what amount of mixture, there will be certain amount of mixture. Let us say this is x1, means x1 means, let us say x is to y. So x portion is air and y portion is fuel or petrol. So the low load, let us say this will be P is to Q. So in this case, P will be air and this will be fuel. So the process of preparing all this mixture according to the load is known as carburation, or the job is done by a carburetor. So if you can see this diagram, just I will explain how this is a simple carburetor and how it functions. Okay, this was covered, so I will just explain it and just listen carefully, because then we'll be analyzing the carburetors, how this carburetor function, how the fuel air ratio is formed. So we'll be doing that derivation. So just listen carefully what happens. Okay, so this is a you can see this is a the carburetor channel through which the air and fuel passes. This is the float chamber, or we'll say where there will be fuel, and this is the way through which the fuel comes. Okay, because let us say the fuel will be in fuel tank. This somewhere here there is a fuel tank, and it is coming here through this channel, and it is just here. This is a fuel valve. Why this is present? Okay, this is a fuel valve. Now why this is present? Because we want a certain level of, let us say this level is H. We want a certain level of fuel always present in the float chamber. Once it comes below this, let us say now the level is here. So this float valve, or this is the float. This is just like how our overhead tank works. If you ever go to your terrace and if you see how your the tank works, it's just like there will be water here and there will be a ball like structure. I know everyone would be knowing, but those who don't know can just follow it up. So there will be just like a ball like structure. This is called the float, and this is a valve, and it will be connected to the pipe. Okay, so as we always want that in the tank this much level of water should be present. Once it comes down, let us say the water comes down to here, so this ball will also come here, so the valve will open, so the water will come inside. Do you understand? The same thing is done here. So as soon as the fuel level comes down, the float valve will come down, and it will allow the fuel to take the place. Okay, so this thing is over. Now through this is a strainer, or let us say any filter. If you see bikes, you can find these air filters, strainer, or let us say this is air filter, because there are many dust particles in the air. We don't want the dust to go inside the engine. So this is, let us say, air filter. You can find it very easily in a bike. From outside only you can see air filter. So this is air filter. Through this, air is taken inside. So what will be the pressure here? It will be atmospheric pressure. And this float chamber is also open to atmosphere. So here also atmospheric pressure. The pressure here will be atmosphere. Everybody is following till here?
Yes, sir.
Okay. So the pressure will be P atmosphere inside the float chamber. Now what happens? Just listen carefully. So air comes through this. I think you might have studied in fluid mechanics venturimeter concept. So the same concept is used in carburetor. So air comes through this, and this is a constriction. You can see that area has reduced here. Earlier the area was, let us say, here it was 100 centimeter square. Now it has come to 50. So the area has almost reduced by half. So what will happen? Area reduces, that means velocity will
Increases.
So velocity increases, then from what we can say is that pressure reduces. Whenever there will be increase in the velocity, the pressure reduces there. The same concept you can see in I can directly say through which formula you find out this one. It is generally Bernoulli's equation P1 by rho g plus V1. Okay. Gz is equal to, let us say, the same three or four things, three things will be there. Let us say this is not applicable. So if pressure, let us say pressure will increase, then velocity has to reduce to make it constant. Okay. So similar thing is available is followed here, where the velocity increases, so the pressure will be lesser than the atmosphere. Let us say here it will be somewhat less than, let us say 0.8 bar. What is the pressure here? 1 atmosphere. Let us say it is 1 bar here inside the fluid chamber. So in this case, the fuel will be traveling through this. This is also called fuel metering orifice. I have already mentioned here, fuel metering orifice. So this, the fuel travels and comes here, mixes with the air, and this fuel are all, I already said one of the properties that they are volatile. They mix with the air and get vaporized and forms a fuel air mixture. Fuel air mixture, and it passes through the throttle valve. After this throttle bar, it goes to the it goes to the chamber, to the cylinder chamber. So this is the whole concept of the carburation. We what we do is we allow the air to pass through a constriction. Because of this constriction, there is a velocity change. The velocity increases, and once the velocity increases, there will be always be drop in pressure. And if there is a drop in pressure, the fuel will travel from the high pressure to the low pressure, and then there will be mixing, because this vapor will get atomized, or let us say it will get vaporized, and there it will form an air fuel mixture. So this is the whole concept of fuel air mixture. Other parts you can see, it is like this portion is generally called venturi or the throat. Okay, just remember this one, because the numerical question that we'll be going to solve ahead will be getting somewhere, some questions are like it is called throat, the venturi diameter. So just remember the name, the terminology. So this is the choke valve, this is the throttle valve. What are it uses, we'll see later. Just remember all this. Okay, so this is the general functioning of a carburetor. So now we'll do the analysis. This derivation was already done in the class. Just I will be overviewing it. I know this was a little bit lengthier derivation, and you might not have followed it up. So just I'm repeating it. I hope everyone follows it up after this. I cover this one. So generally, we'll start with, see, two mass for to calculate air fuel ratio. We need to have mass flow rate of air and mass flow rate of fuel, correct? So let us first calculate mass flow rate of air, then we'll calculate mass flow rate of fuel, then we'll take the ratio. That's all thing. That is the thing that we generally do it. Okay, so we apply here first law of thermodynamics in an open cycle. First law of thermodynamics in an open system, sorry, first law of thermodynamics, or we generally call it as steady state equation. I hope everyone remembers this formula. H1, what is H? Enthalpy. What is C1? Anyone? What
No,
is
sir.
C1? What?
Don't know, sir.
Okay. So this is so everyone is in the third year, right? So you might have studied SFE, steady state, SSE, steady state energy equation. Okay. So we are calculating the steady state energy equation at the two locations, at location 1 and location 2. So just listen carefully. Okay, so here, when the air is here, what is the pressure? Sorry, what is the enthalpy here? Air we are assuming as ideal gas. So just note it down, that what are the assumptions that we are taking. We are considering air as ideal gas. Okay, so what is the energy content here? Enthalpy plus it is coming with certain velocity. So let us say it is c1 square by 2. Okay, this is the kinetic energy, correct? We generally do it half mv square is the kinetic energy. So we are all considering the specific properties here. That is why we have not multiplied m. Okay, so c1 square by 2 plus q. What is q? It is the heat transfer. Then h2 is equal to h2. Same will be doing here, h2 plus c2 square by 2 plus w. What is w? This is the work transfer. Whether we are doing, we are supplying any work, whether the work is being transferred through this boundary or not, that we are doing. Okay. So now next step. So one of the assumption that I've already said, first assumption is that this is ideal gas. Okay. Then is there any heat transfer and work transfer here? Just tell me.
No, sir.
It's not there. Okay. So this q is 0, w is 0. So the next step will be h1 plus c1 square by 2 is equal to h2 plus c2 square by 2. This is the only remaining. Now the pressure here is atmospheric pressure. Okay, PATM. Okay, so the velocity we generally consider it here is like the velocity of normal air and which is stagnant. So the C1 we consider it as 0. Okay. Next, our next assumption was work and heat transfer and work transfer. Heat and work transfer is negligible or 0. Because you might say there will be some energy, there might be some heat coming through the ambient. So it is negligible. Then C1 is coming to 0. As I am telling, because this is stagnant air, because air is at atmospheric pressure, we are considering that it is stagnant, and that is why C1 is 0. So the next step, what we are getting, what is C2 then? C2 we are getting this one, correct? Everyone followed it up, how C2 is equal to root over of 2 H1 minus H2, correct?
Yes, sir.
Okay. Then I have already said this is an ideal gas. So in place of H1, can I write CpT1? I can write, right? Enthalpy
Yes,
is
sir.
equal to CpT1, CpT. So Cp T1 minus T2. That is the that we got. So the whole equation is now 2 Cp T1 minus T2. Then let us take T1 outside. So it will be 1 minus T2 by T1. Now we have taken heat heat transfer is negligible. So let us say this is an adiabatic. So we'll use adiabatic equation of ideal gas PV to the power gamma is equal to constant. So what is the relation between T and P? Just mention in place of V, write T by P to the power gamma is equal to constant. Last class I already said this one. So it will be T to the power gamma P to the power gamma minus 1 is equal to constant. So in place of T2 by T1, what can I write? It is P2 by P1 to the power gamma minus 1 by gamma. So that is what I have substituted here, correct? Everyone followed it up, how this happened?
Yes, sir.
Okay. Then this one we got the velocity at the throat. The velocity at throat is C2 here. So we got the value here. Now how to calculate mass flow rate from velocity? Simple, right? Rho A V. How this is velocity. How did it come? Mass is equal to density into volume. So density is equal to area into velocity. In place of volume, I wrote because this is volume flow rate. That is why area into velocity. So you get rho 2 A2. What is A2? A2 is the area of the orifice. Okay. So rho 2 A2 2 CPT1 1 minus this one. Okay. Now one more thing to note here is that this is in actual case we multiply a discharge factor, coefficient of discharge we say it, just to take the care of there will be some losses due to friction and all. We call it coefficient of discharge. Okay, so this is CD. How did this one come? So in place of rho, just listen very carefully. So can you write, we know PV to the power gamma is equal to constant. In place of V, can I write P by rho to the power gamma is equal to constant? This is, let us say, specific volume. Specific volume is V by M. What is M by V? Just the reciprocal of it. What is it? Density. So P by rho to the power gamma is equal to constant. From there, I calculated what is rho 2. Rho 2 is rho 1 into P2 by P1 to the power 1 by gamma. Sorry about the space. So rho 2 is equal to rho 1 P2 by P1 to the power 1 by gamma. Okay, everyone followed it, how I wrote this one?
Yes, sir.
Okay.
Yes, sir.
Okay, in place of rho 1, what I can write? In place of rho 1, so everyone knows the formula P is equal to rho RT. Let us say if you write in, this is molecular mass, rho, we can write like this. So just substitute P, so rho is equal to P by R. This is not a universal gas constant. Here it was universal gas constant. Ru by the molecular mass is the gas constant. So P by RT. That is what I have substituted here. In place of rho 2, I have written rho 1 into P2 by P1 to the power 1 by gamma. And that in place of that rho 1, I have written P1 by RT1. P1 by RT1. The T from the inside the root comes outside. So it will be root over T. So root over T, here it is T. So that is why in denominator you can find there is a rho T1. And the P2 by that ratio, P2 by P1 to the power 1 by gamma goes inside. Here it goes to square 2 by gamma and gamma minus 1 by gamma. So here if there will be addition of 1 by gamma, we'll get this one. Okay. 2 by gamma, because it is going inside the. So here you get the formula. Everyone understood what is that, how the derivation is done?
Yes, sir.
Okay.
Yes.
Then we calculate the fuel, how to calculate the mass flow rate of the fuel. Now, one of the main assumption, the difference in assumption, I missed here, is that air is considered here compressible, because air is a gas. There is every possibility that the density will change, okay, over the temperature when pressure is applied. But fuel is a liquid. It will get vaporized eventually, but still it is a liquid. That is why we consider it as incompressible. And when we consider it as incompressible, we can directly take into consideration the use of Bernoulli's equation. Bernoulli's equation. Okay. Now, what is Bernoulli's equation? I hope everyone remembers P1 by rho g plus V1 square by 2. Okay. Okay. 2g. V1 square by 2g plus z. Okay. These are all in the form of head. Means the unit will be in meter. V1 square by 2g. Here, this one also meter. This one also meter. So we have just applied the. Here the 1 and 2 has changed. The 1 is here, where the fuel is there. That is 1. and the location 2 is at the orifice, and the height is Z. Now, one of the things, please note carefully, is there is always a difference of height between the fuel surface and the point where the fuel is discharged. This is knowingly only maintained because let us say there will be a certain if the fuel was still here. So here also there will be fuel. So if there is even a little bit of pressure difference, the fuel will be overflowing from here. That is why we don't want that. So we generally have a height difference. So directly we can write here P1 plus 0.51 C1 square plus by P2 by rho f. What is rho f here? Density of the fuel. It is constant. That is why I've kept it constant. 0.5 C2 square plus GZ. Here also we are taking C1 as 0. This is 0. Okay. Because that, as I've already said, the here atmospheric pressure is present. So we consider the air is stagnant. So C2 is 2 into P1 by rho f minus P2 by rho f minus GZ. Everyone understood how it came? Okay. Now same how to calculate the mass flow rate? It is rho f into AF into CF. Okay. What is AF? AF is the area of this orifice outlet. This is the area. Let us say the diameter will be D. So we'll be directly calculating pi by 4 dF square. Okay. So rho into AF, P1 by rho F, P2 minus GZ. So again, this one rho F will go inside and this denominator will get cancelled. One rho F will stay outside, another rho F will be multiplied here. I hope this is very easy, just normal algebra. So after that, so then we calculate the fuel air fuel ratio, mass flow rate of the air by mass flow rate of fuel. So this is how the formula has come. No need to remember this big formula if you just understand how this is derived, because once you derive everything, you will automatically remember the formula, because this is general just this is that one is steady state equation and this one is just Bernoulli's equation. So you can directly derive at the same whenever you do any calculation. But if you want to do it, solve it faster, just remember this is just simple formula. This is, let us say, delta P minus rho f GZ. That's all. 2 into rho f. That's all. Okay. So I hope you understood this derivation. Then we are coming to, there are three types of processes that we generally encounter. One is idling, one is cruising, another is power ranges. So what is an idling? Idling means what do you mean by idle? It is idling. What do you mean by idle? Someone is sitting idle. What does that mean? Just someone respond.
No work done.
No work. So no work done. Or let us say someone is just sitting just sitting and not doing any work, and so the engine also, there is a point where it is idling. It is going through an idling cycle. What is that cycle?
Efficiency will be 100%.
Sorry.
Idle means where efficiency will be 100%.
No, not particularly. Idling means what is happening is, here the engine has started functioning, but the vehicle has not moved. Engine is running, but the vehicle has not started moving. Just before the start of the cycle, start of the combustion cycle. Okay. Engine has one, vehicle has not moved. Okay. That portion is idling cycle. Now just listen carefully what happens in idling cycle, and you yourself will answer what is the air fuel ratio that is maintained here. I have already mentioned that rich means more amount of fuel quantity will be there. As I said that engine is running, vehicle has not moved, then you might be thinking that okay, we don't need rich mixture, we only need a lean mixture, but that is not the case. There is a concept which is called dilution of charge. What is this? This one is already covered in the lecture. I will say it briefly. So let us say this is engine and the previous cycle was exhaust. exhaust stroke. So still there in this clearance volume, there will be some exhaust gases already will be present. And the pressure, let us say, will be, let us say here it is 1.2 bar. And this is the inlet manifold. And here it is carburetor. Okay, this is carburetor. This is inlet manifold, and here is the throttle. This is the throttle valve. Okay. So just when the throttle valve opens slowly, there is a minor opening. Let us say the throttle valve has just opened. So there was some air present earlier, but here now air is not present. So there will be a condition called vacuum. A vacuum will be created, and the pressure here will be lesser than 1 bar. Let us say it is somewhere around 0.8 bar. So now what will be happening is the exhaust products will be moving here. This is all taking place when the piston is still at the TDC. It has not started to move down, because when it starts to move down, the pressure will reduce here, and then again the fuel will come inside. But before that, just before that, there will be a condition when the pressure at the upstream will be lesser than atmospheric pressure, so the air will be moving out. Sorry, the exhaust products will be moving through this, and that is why the fresh charge is diluted. That is why called dilution of charge. This is called dilution of charge, and for this we supply a little bit richer mixture. Means that is fuel quantity is increased. Rich means fuel is more in that air fuel ratio. Fuel is more. That is why in idling cycle you can see it is richer mixture. Then next comes the powering. Powering cycle, it's very obvious that in powering cycle we need more power, so you need more fuel. Other than that, one important reason is that if there will be more fuel, the temperature of the engine is, fuel is more, the temperature of the engine will reduce, because after a certain temperature, the valves might get damaged. That is why we don't want the valves to, the temperatures to increase after a certain limit. So we supply more fuel. So then the temperature in the engine will reduce. Now you might be telling this is very confusing. How, if there is more fuel, then the temperature will reduce? It should increase because there will be more combustion. No, this is not the case, because whenever there is combustion, this let us say there will be some fuel coming, and still there are some particles which are in liquid form. This will get vaporized, or this will get evaporated. So if it will get evaporated, it will carry the latent heat, and thus the temperature will reduce. Understood how why the temperature is getting lesser at higher power? That is why we supply it rich mixture. Everyone understood?
No, sir. Please explain again.
Okay. So generally what is happening in high power is that we are supplying richer mixture. Now why this is so? Because all the fuel that is coming through the carburetor, some might be in the liquid form. Okay. Everything might not be getting vaporized or atomized. Okay. There might be some fuel which is in liquid form. And when it is liquid form and there is certain temperature or certain heat, this liquid will get vaporized. Okay. Just simple concept. What I will say, you drink. Do you know that the water kept in a earthen pot is cooler, and we drink the water from earthen pot during summer? Why it is so? Everyone knows this one. Huh? Why the water in the earthen pot is cooler? Just respond whether you know it or not.
No, sir.
No, sir.
Okay, earthen pot. If you see in earthen pot, in mud pot, the water stays little bit cooler. This is because the water particles that are present on the surface, what it will be doing is it will be carrying the heat that is already present inside the liquid, and it will evaporate. How does the liquid changes into vapor? whether we increase or we provide the heat or we take away the heat. What do we do so that a liquid changes into vapor? Just tell me. We provide the heat, right? When we boil the water.
Provide the heat.
Exactly that same thing is taking place at atmospheric pressure in an earthen pot. That is why so there is a difference between boiling and evaporation. You just this is very basic thermodynamics. What is the difference between boiling and evaporation? You go and refer that one, you will understand. So in evaporation, what happens is that the fluid particles will be carrying away the latent heat. It will carry the latent heat and the liquid will be getting converted into vapor. And it will form water vapor. That is why you can find that the temperature is slightly lesser and we get cooler water in from the earthen pot. The same concept is acting here. When there is a engine, the fuel is sprayed here. The excess fuel that is sprayed is in form of liquid, and it is just taking away the heat, and it is getting vaporized, and it is mixing with the air. So that heat that is taking place is enough to reduce the temperature of the engine and to protect the valves. Now now it is clear, right?
Yes, sir.
Okay. And then is the cruising. Cruising is just normal, and this is the portion of the operation of the vehicle where we want the maximum economy, or the fuel economy should be enhanced here. So that is why we provide lean mixture. So this is very general. Then we'll move ahead. Then as I said, there are two valves already present. Now, what are their function? We'll just go through it briefly. So this one is the choke, and this one is throttle. This is choke valve. This is throttle valve. Now, what is its function? I will tell you. When choking is used, you might be driving bike. Just tell me, when do you press choke? When do you use choke? Any idea? You might have used, just you don't know the reason. That might be the case. But have you used a choke valve or not? When you use scooty or use bike? Just respond.
No, sir.
You have not used?
Yes,
Okay.
huge, sir.
Used. But the main reason what is that when we press that switch, what is happening is that this choke valve will close or it will slightly open. Generally, we do it in winter. In winter season, generally what happens that engine is already very cool. Generally in winter season, engine is already very cool. So the vapor is not getting enough heat. The fuel is not getting enough heat to get vaporized, to form vapor and to form an air fuel mixture to get combusted. This is not happening. That is why we have to, what we have to do, we have to supply more fuel. We have to supply more fuel. And how this can be done? This is done by when you press that choke switch. What is happening is the valve is closed here. Now, once the valve is closed here, see, in a closed chamber, whenever it will be closed, the air is not flowing through it. Then what is there? Vacuum. So as it is closed there will be some vacuum created here. There will be some vacuum cleared here, or there will be slight, very low flow of air, but still there will be some vacuum, and the pressure here will be lesser than atmospheric pressure. And this is when the fuel comes out. Fuel comes out and goes, and we get a richer mixture. And thus we can start the vehicle when it is in winter season. Okay, that is the function of a choke valve. Throttle valve is generally used for let us say to get high power, or if you open it, if the throttle valve is fully open, then what will happen? Air will flow maximum when throttle valve will open. There is no restriction, so air will the more amount of air will get inside here. The velocity will be higher, pressure drop will be higher, so fuel will be coming, so we'll get more power. So when the throttle valve is full open, we get richer mixture. Okay, so we get a richer mixture when the throttle valve is fully open, and In that is what is the use of the throttle valve. We control the valve positioning in such a way that we want this much amount of flow rate of air should come, and this much pressure drop should be there, and this pressure drop governs the flow rate of the fuel, and thus we generate air fill ratio. Okay, so this is all about the summary that are already covered. They will go to solve some few numericals. Okay, so now everyone can see the screen, right?
Yes, sir.
Okay, so we have some numericals, so I hope everyone is having calculator with them. Okay, so the first question is, for the same power, same maximum power, pressure and temperature, which one of this is true? Just tell. I hope how many people are present? Oh, just 4. Okay. Just tell me what is the answer of this. So I just covered it, this one, right? For the same maximum pressure and temperature, which cycle is more efficient? Huh?
Auto cycle, sir.
Or same maximum pressure. Pressure ratio is, I am not telling the compression ratio is higher.
So diesel cycle is more efficient
So
than
diesel,
auto cycle.
diesel.
Yeah. So the answer is diesel. Yes. So the answer is diesel. Because if the compression ratio was constant, then Otto cycle would have, efficiency of Otto would have been higher than the efficiency of diesel cycle. Okay, so we'll go to the next question. Just answer this one. Which of the following is or are correctly represent the equivalence ratio? I have not covered, but the equivalence ratio was covered in the slide, in the lecture. What is equivalence ratio? Generally refer by phi. What is equivalence ratio? Do you know or not?
No, sir.
It is the ratio of actual fuel air ratio by stoichiometric. What is stoichiometric ratio? So are you seeing the lectures or are you just attending the live? Just be honest whether you are attending, seeing the lectures or not.
Yes, sir. I seen the lectures.
Okay, so it was conveyed there. So actual, it is the ratio between actual fuel air ratio by stoichiometric fuel air ratio. So one option is this one. Which one is that? Actual fuel air by stoichiometric fuel air. A is correct. And if we reverse the ratio, let us say now we want in terms of air fill ratio. So what would be the answer? So in the numerator, it will be stoichiometric, right? Correct. So B is correct. Now just solve this question. I have already told the formulas. A simple jet carburetor has to supply 5 kg of air per minute. So what is given? Just write whatever thing are given. Just take that one. Then you can start solving. A simple jet carburetor has to supply 5 kg of air per minute. So what is given? The flow rate of air is given. 5 kg per minute. Now the air is at a pressure of, so this is the atmospheric pressure that is saying is how much? 1.013 bar 1.013 bar, and temperature is 27 degrees Celsius. Okay, and the air velocity is 90 meter per second. Which velocity is mentioning it here? 90 meters per second. Where it is possible? You tell me. At which portion of the carburetor? Hmm? Such
After
high
fuel
velocity.
mixture.
It is at the throat. It is at the venturi of the throat. So you have C2, or let us say, yeah, C2. C2 is 90 meter per second. What will be the value of the pressure at the throat? It is asking P2. Okay, it is asking P2. This one is P1. Everyone understood the question? I'm giving you, let us say, 2 minutes. Just try to solve this question. I will again open the slides. You can take the formula from there. At least you attempt to solve the question. That will really help you. So just this one, air. Everyone can see the screen, right?
Yes, sir.
Yeah, just solve it. I'm giving you 2 minutes. It's very easy question. Are you attempting? Did you attempt it?
Yes, sir.
Yeah, good. Yeah, just give it an attempt. Let's see. So did you find what is the pressure? It's a direct formula. Yes. Did anyone was able to solve it?
You're trying, sir.
Okay. Just 1 more minute I'm giving you. Okay, just see now. Okay, so it is air, so nothing is mentioned. So just take file like this. So H1 plus C1 square by 2 is equal to H2. Unless mentioned, don't take heat transfer and work transfer by 2. Okay. Now, what are the values that are given? C1 is 0. C2 is given. H1 is given or not? H1 is given, right? CPT1. In place of H1, you can write CP into T1. H2, you can write CPT2. C2 is how much? 90. 90 square by 2. So from here, you can find 2 into CP in T1. You have to find T2, right? Minus 90 square by 2 by CP is equal to T2. Just tell me in what is the value of CP? It is air, right? So 1005 joule per kg. T1 is how much temperature it is given? 27 degrees Celsius. So it is 300 Kelvin minus 90 square by 2 by Cp is 1005 is equal to T2. Just calculate how much are you getting T2. Just I will calculate.
Five nine to 1.9.
How much?
5 9 to 1.9.
Temperature would increase. Are you sure? Just see the formulas correctly. I think you have done some mistake. I think you are doing some mistake. Let's try to refer again. Okay, I think the okay, this 2 will not be there, right? We already correct.
To multiply, we already.
Yeah. So that mistake, that is a silly mistake we did. So it will be like CPT1 minus 90 square by 2 by Cp. Just do it 1005 into 300 minus what is 90 square? 8100 by 2 by 1005. How much are you getting?
295.9.
295.97. This is in Kelvin.
Yeah.
Okay. Then you can directly apply your adiabatic formula. So T2 by T1 is equal to how much? P2 by P1 to the power. Here it is gamma minus 1 by gamma. So when it will come this side, it is gamma by gamma minus 1. So from here, calculate what is P2. P1 is given 1.013 bar. Calculate what is P2. So T2 is 295.97 divided by 300 to the power 1.4 divided by 0.4. Okay. So it will be somewhat coming 0.95 into 1.013, which is equal to 0.966. Did you get this one? 0.966 bar.
Yes, sir.
So the option is C. Okay. Then this one I already covered. So just tell me the answer. For idling system, what is the case? A, to compensate the dilution of charge. For cold starting, for meeting maximum range of operation, for meeting rapid opening of throttle. Tell me. What is idling? Just I covered.
For cold starting.
Idling is cold starting. That is choke. For cold starting, winter I told you use choke. So 4 is B. 1 is, what is idling? This is the thing I covered or not? Dilution of charge. So 1 is A. What economizer I have not covered. Economizer, don't go with the name. Economizer is used for power enrichment. Whenever we need higher power, we use economizer. What is the function of economizer? So generally, what happens is that during power enrichment, the throttle is fully open. Just imagine this is the carburetor. This one is also not covered in your lecture. So just listen carefully. Whenever the throttle valve is open, no, throttle valve is suddenly opened because we want high power. So whose inertia will be more? Air inertia will be more or fuel inertia will be? Let us say here it is
Air.
air is coming. Air inertia will be more. Fuel inertia will be more because whose mass? Air is a gas, right? So air, the inertia of air will be lesser, so it will come, but fuel's inertia will be more. So it will be somewhat the velocity or velocity will be lesser or the mass flow rate of air will be lesser. So there won't be any proper mixing. We cannot forget our required air fuel ratio. That is why what happens is we enrich, we provide more fuel. We provide more fuel in case of the economizer's function is to provide more fuel or to enrich the mixture. And when it is done, when there is this one for meeting the rapid opening of the throttle valve. So 2 is okay. So it is maximum range of operation because you will somewhat get confused between economizer and an acceleration pump. The same thing happens with acceleration pump also. Acceleration is generally a transient process. Okay, it will be taking place over a period of time. So there will be a time factor introduced here. So when there is a over a period of time, so the throttling, whenever the what will be happening is the throttle will open over a period of time, and then there will be a difference of inertia. So 3 is C, sorry, 3 is D, and 2 is C. So the answer is B. Just remember all the functions, then you can answer this type of question. Not a big deal. Question number 5. For an IC engine based on ideal Otto cycle, the increase in the compression ratio leads to what? Decrease in the thermal efficiency and mean effective pressure. Decrease in the thermal efficiency but an increase in mean effective pressure. An increase in the thermal efficiency but decrease in the mean effective pressure, or the increase in thermal efficiency and increase in mean effective pressure. What is the right answer? It should not take so much time.
D, sir.
D, correct. So no need to explain here. We'll move to next. A simple carburetor suffers from, this one is already covered. I think you can refer the lectures. This one is already covered directly. All these 4 points. A simple carburetor suffers from the fundamental limitation, which are as follows: increasing the richness as the engine speed increases. In simple carburetors, that is why there has been several modification in a simple carburetor. So this one is already mentioned in mentioned in other lectures. So all the reasons are correct. Then we'll go to the next question. Which of the following can be reason for using a choke in an automobile engine? Just tell me. This one we just covered now.
Cold starting.
Yeah. Starting in cold weather. Then now this is a easy numerical. I hope you can do it. Just I'm giving you 2 minutes. In an idle Otto cycle, the air at the beginning of the isentropic compression, we have P1. P1 is 1 bar. T1 is 15 degrees Celsius. Ratio of compression is 8. The heat added during the constant volume process, QS is given, is how much? 1000 kilojoule per kg. What is heat rejected? Calculate. Do you know how to calculate this one? It's very easy question. Last class we have covered this one. Do you know or not?
No, sir, I didn't attend the last class.
Okay, so try to attend all the lectures. So the what is formula for a Otto cycle? 1 minus 1 by RC to the power gamma. So 1 minus what is RC? 8 to the power 0.4. Calculate how much is the efficiency. How much? Somewhat around 56.47%. Am I right? Did you get this one? Are you listening?
Yes, sir, 0.5647.
So efficiency also we can write 1 minus Q rejected by Q supplied. So 1 minus QR by QS is equal to 56.47%. How much is QR? QS is given. How much is QR? Calculate. Just subtract 56%. This is in percent, okay? So it will be 1 minus 0.435. 0.435 you will get into how much is the constant volume heat addition? 1000. Q supplied is 1000. So how much? 435. Somewhat around 435 kilojoule per kg you will get. Correct? You understood this one? Just respond.
Yes, sir.
Then the next, keeping the other parameter constant, the brake power of a diesel engine can be increased by. This one I covered in the first lecture itself. Keeping the other parameter constant, the brake power can be increased by. This is directly increasing the pressure of intake air, and this process you will be studying. It is called supercharging. Just remember this term supercharging. What is done in supercharging is that we pressurize the air. We pressurize the air. Okay, we pressurize this air and we supply it to the cylinder. Now what this will be doing, it will be in means if we increase the pressure, so what will happen in a volume, let us say the volume is constant. If we pressurize a certain thing, then more amount of that we can cover, correct? For example, earlier you could just at normal pressure, let us say 1 bar, some gas was there. This is at 1 bar. Now same container volume is constant. This is V1, this is V1, but the pressure has increased to 10 bar. So whether the gas amount will increase or it will decrease or it will be constant. Answer.
Sir, can you repeat, sir?
There are two volumes. One is let us say there are two volumes. V1, both are the same volume. Let us say 10 centimeter cube, 10 cc, 10 cc engine. One is at pressure 1 bar, one is at pressure 10 bar. In which case the amount of gas present in that cylinder will be higher. When you
10
pressurize,
bar.
yeah, when you pressurize, the mass quantity of gas will increase because the molecules of the gas will come closer and you can occupy more gas. So that is why NV increases, volumetric efficiency, and thus in that way we can find that the will be having more efficiency. So the answer is increasing the pressure of intake air. Then the next is the volumetric efficiency is affected by exhaust gas in the clearance volume, the design of the intake and the exhaust valve timing, all of the above. Just answer from just basic knowledge. When will the volumetric efficiency increase? What is volumetric efficiency? First of all, tell this one. I hope you remember it is actual mass of air that is stored in the cylinder by the displaced. I am writing in mass, you can write in volume. Actual volume by displaced, thus, or the stroke, the total amount of volume, swept volume, we call it. Okay. So if the exhaust gases, there are some exhaust gases in the clearance volume, so volumetric efficiency will be affected or not? You tell me. If a certain cylinder's volume is 10 cc and some amount is covered with exhaust gases, let us say this is two exhaust gases, it is covering 2 cc. Obviously the volumetric efficiency will reduce, right? Because we cannot contain that much amount of it. Yeah. So this one is correct. So that, yeah, all of the answer is the right answer. The design of the intake and exhaust valve. See the intake and the exhaust valve, if will increase the size, then that much amount of volume will be gone. So this is also one of the reason. The valve timing. That is why to increase more amount, so that more amount of air is air, or let us say the charge is inside the cylinder. That is why we manage the valve timing that we have already covered. So the answer is all of them. Then we come to numerical. I think there is some, this image has just, okay. So this is a question on dual cycle, the simple cyclic engine. Just tell me, just reading the question, whether you can solve or just I should start solving. The air standard dual cycle has a compression ratio of 10. The pressure and the temperature at the beginning of the compression are 1 bar and 27 degrees Celsius. The maximum pressure reached is 42 bar and the maximum temperature is 1500 degrees Celsius. Determine the temperature at the end of the constant volume heat addition cutoff ratio, work done per kg of air, the cyclic efficiency. Tell me. I'm giving you 1 minute. Just tell me whether you can solve or we should start solving.
Please solve, sir.
Okay. But not only me, you also solve. Just take help and solve. Just not like you are just sitting idle.
Okay, sir.
Okay. So any questions whenever you are solving thermodynamics, just because there are so many values, you will get confused for sure. So what you need to do is first, whether you understand the question or not, just write given. The air standard dual cycle has a compression ratio of 10. So first of all, RC is equal to 10. What is RC? I told it is, this is P versus V. Okay, it is V1 by V2. Correct. This much you know. Then the next line will read the pressure and the temperature at the beginning of the compression. So P1 is 1 bar, T1 is 300 Kelvin. The maximum pressure, where is the maximum pressure reached? Just tell me from the graph.
3.
3. So P3 is equal to P4 is equal to how much? 42 bar. Where is the maximum temperature? T.
4.
Yeah, correct. So T4 is how much? 1500 degrees Celsius. Always mention in Kelvin. So it is 1773 Kelvin. Okay. This much is given. Then you start the temperature at the end of constant volume heat addition. So what is asking? Constant volume after, what is the temperature after constant volume heat addition? It is T at which point? T at constant volume heat addition and shear. So it is T3. It is asking T3. Correct? Because T4 you know, right?
Yes, sir.
Okay. So the what are the other things? That is cutoff ratio. What is cutoff ratio? It is represented by beta, represented by V4 by V3. This one we have to calculate. And what else? Work done. Then we have to calculate work done. Then we have to calculate cyclic efficiency. Cyclic efficiency. So this is a dual cycle. See, others we already have formula directly. We can take that formula, help of that formula. For dual cycle, I suggest not to remember any formula. Just try solving each temperature at each portion. So we already have T1. Can we calculate T2? Can we calculate T2 or not? What is T2? T2 is equal to T1 into, tell me. It is adiabatic process, right? PV to the power gamma is equal to constant. In place of V, in place of P, replace P by V. V to the power gamma is equal to C. So T V to the power gamma minus 1 is equal to constant. So T2 is equal to T1 V2, sorry, V1 by V2 to the power gamma minus 1. So what is T1? T1 we have 300. What is V1 by V2? We already have. What is the compression ratio?
10.
10. So 10 to the power 0.4. Tell me what is this much. You solve and tell me what is T2. Are you solving? Tell me.
753.56.
Yeah. 753.56 Kelvin is T2. Then we will calculate T3. How to calculate T3? What is the process that is taking from T2 to T3? Tell me. It is constant volume process.
Constant volume process.
So we have to apply this one. T3 by T2 is equal to T3 by P2. Correct?
Yes, sir.
So do we know P2 or P3? Do we know or not? We don't know.
P1, sir.
So we know P1. P1 is equal to 1 bar. Can we calculate P2? Hmm? How to calculate P2? You tell me. Direct P1 into V1 by V2 to the power PV to the power gamma constant, right? That is the formula from here. So P1 is 1 bar. It is 10 to the power 1.4. What is P2? You tell me.
25.11.
Okay. Which is 25.11
Right.
bar. So P2 we got. P3 we have or not? P3 we have. It is 42 bar.
42 bars.
Okay. So it is 42 by 25.11. What is T3? T2. T2 is 753.56. From here we will get T3. Calculate T3. How much is T3? Are you getting 1260 point?
1260.43.
Correct. It is coming 1260.43 Kelvin. Okay. So T3 is clear now. So first we have solved T3. Then it is asking beta. What is beta? V4 by V3. Just use common sense. Okay. How to calculate V4 by V3? So V4 by V3. How to calculate V4 by V3? You tell me. It is a constant pressure. So V4 by V3 will be equal to how much? P4 by P3, right? Sorry, P is it is T4 by T3. Correct? You understood?
Yes, sir.
This is constant pressure. So V is directly proportional to T. So what is T4? 1773. What is T3? 1260.43. Calculate. What is V4 by V3? How much is beta you are getting? I think 1.441, 406. 1.406, right?
Yes, sir. 1.406.
Okay. So next question, what is asking? Work done. How to calculate work done? Just calculate Q supplied minus Q rejected. It is the net work done. What is the Q supplied? CV into T, how much? T3 minus T2 minus, sorry, plus this is constant volume heat addition. Then the constant pressure heat addition. T4 minus T3 minus CV. What is Q rejected? T4 minus T1. Okay. Only thing that we don't have now is T4. Sorry, T5. This is the process, right? This is the process where heat is rejected. So it is T5 minus T1. How to calculate T5? You tell me.
So it's a constant volume process, so we can take it from there.
Okay, so you are telling we'll calculate T5 by T1. We know that T5 it will be constant volume process, so P5 by P1. This you are telling, right? Do you have P5?
No, sir.
So how to calculate P5? You tell me. You know the pressure here. It is 42 bar. Okay. You just need to have what is V4 by V5. How much expansion is taking place, and that is very simple because just I will tell one simple formula. You see, this is the cycle, right? This is the cycle. This is 1, 2, this is 3, this is 4, this is 5. So what do we want? We want V5 by V4. Okay, how to calculate V5 by V4? Just make some few arrangements. In place of V5, can you write V1?
Yes, sir.
Now can you divide V2 and multiplied V2? Understood? Correct, right?
Yes, sir.
So what is V1 by V2? Is compression ratio. What is
Yes.
V2 by
10.
V4? In place of V2, can you write V3? V2 is equal to V3.
Yes, sir. It is.
V3 by V4, it is 1 by beta. So RC by beta, you remember RC by beta is equal to RE. RE is the expansion ratio. That is V4 by V5 by V4. This one you remember. So we have RC 10, we have beta 1.4. Just calculate how much is 406. So how much is RE? Calculate fast. We have
7.11.
7.11. Now you have this V5. Can you calculate P5 now? So
Yes,
P5
sir.
is P4, V5 by V4 to the power gamma. Calculate what is P5.
Sir, what is P4?
P4 is same as 42, right? See, I did one mistake. You didn't say me. So it is P5. We have to calculate P5. P5 is equal to P4. It is V4 by V5 to the power gamma. P4 is 42, right? Maximum pressure 42 bar it is given.
Yes, sir.
So V4 by V5 is 1 by 7.11. 1 divided by 7.11 to the power 1.4 into 42. How much you are getting? 2.69 I'm getting. Are you getting that much? Did you get that much?
So guys are trying calculating.
Then calculate T3. Sorry, what do we have to calculate? T5. Calculate T5 from there.
So 807.
Correct. Now calculate what is the work. Q rejected you will get is how much? I got 364.69. Q supplied you calculate. How much you are getting?
They're doing so.
You'll get somewhere around 878. Just I will. We're running out of time, so you'll get somewhere around 58 to 58.4 efficiency. You will get is 0.584. Okay, 58% somewhere around that. And if you'll calculate
Okay.
this one, you will get work. Okay, this subtract Q supplied minus Q rejected, you will get the work. Okay, you understood the question? How to solve?
Yes, sir. Yes, sir.
Okay, the next question, we will go fast. For an engine working on an ideal dual cycle, the compression ratio is 10 and the maximum pressure is limited to 70 bar. If the heat is supplied is 1680, and find the pressure and the temperature at various salient points of the cycles and the cycle efficiency. The pressure and the temperature, the commencement of the compressor. So can you do this question? First of all, which the question is of ideal dual cycle. So just draw a dual cycle. This P versus P dual cycle somewhat looks like this. Sorry. Okay, it looks like this. Oh,
Yes. So it's
this
a
is,
dual cycle.
yeah. Okay, just I will repeat it once again. Just I'll do it properly. I think this is just repeated question. Okay, so this is P versus V. Just do it like this. Just this is 1, this is 2, this is 3, this is 4, this is 5. Okay, now what it is asking, compression ratio. So we have V1 by V2 is equal to 10. This is given. Maximum pressure is limited to 70 bar. So we have P3 is equal to P4 is equal to 70 bar. Correct. This one we have heat supplied is QS 1680 kilojoule per kg. Okay. Find the pressure and the temperature at various salient points. The pressure at the temperature, it has given P1. Same as the previous question, correct? Correct or not? Same as previous question.
Yes, sir.
You will be able to do, right?
Yes, I will try, sir.
Yeah. See, very simple. P1 is given, T1 is given, V1 by V2 is given. So you will be able to find T2, correct? Then you can find T3. Okay, because QS is given 1680. Even you don't have to. What is QS? QS is CV into T3 minus T2 plus CP into T4 minus T3. This is equal to 1680. See, maximum pressure. So we have P3. P3 is equal to how much? 70 bar. Can we calculate P2 now?
Yes, sir.
Can directly calculate P2 by P1, V1 by V2 to the power 1 by to the power gamma. From here you can calculate P2. It will come, let us say, some value. From there P2 you can calculate. Once P2 is done, then you can calculate the temperature. Okay, because T1 is there, you can also calculate T2. You'll get
So I'm
T2
getting
from the
936.93 for T2.
T2 you will be getting how much you are telling?
936.93.
P2 or T2?
T2, sir. Temperature.
No, I think you have done some error. No problem, you can solve it later. You understood the question, right?
Yes, sir.
Okay. So you solve this question. Once you get T2, then you can find T3, T4, and then T5. So you get the temperature and pressure. First bit is done. Then the cycle efficiency is very simple. Q supplied minus Q rejected by Q supplied. Just do this one, you will get efficiency. That's all. Then we can move to the next question. Then okay, this question, an oil engine works on a dual cycle, the heat liberated at constant pressure being twice that liberated at a constant volume. So it is given, let us say Q supplied at constant pressure is twice at that as constant volume. Okay, compression ratio RC is 8. Okay, expansion ratio RE is 5.3. Only change that is done is here is PV to the power 1 by 3. Sorry about this. It is PV to the power 1.3 is constant. Only you have to follow now gamma. You have to take n is equal to 1.3. You cannot take gamma is equal to 1.4 now. You have to take 1.3. Cp is given, Cv is given. That is very sure. And the T1 and T2 is given. So T1 is given as 300 Kelvin. T1 is given 1 bar. Okay. Can you solve this question?
Yes, sir.
Same question, just they are framed in a different language. See, this is somewhat like this. Just draw the PV diagram. 1, 2, 3, 4, 5. So it is saying that Cp T4 minus T3, we are getting a relation that 2 into Cv into T3 minus T2. We are getting a relation somewhat like this. We have T1, we have 8. So we can calculate T2. Okay. So T2 can be calculated from here. Then we have RC and RE. Can we calculate beta? RC into RE will give,
Yes,
I've told the formula. RC by beta is equal to RE.
RE.
So beta can be calculated RC by RE. So once that is known, you have all the ratios now. You have V3 by, you can P3 by P2, you can calculate. You can calculate, you already have T4, V4 by V3. Using this, you can calculate all the temperature and pressure. Okay. Just remember to use n is equal to 1.3. Now we'll do some questions on carburetor. So similar question we have solved, but I think it is related to solve one question at least to have a basics clear. See, a simple jet carburetor is required to supply 5 kg of air and 0.5 kg of fuel per minute. So mass flow rate of air is given 5 kg per minute. Mass flow rate of fuel is given 0.5 kg per minute. Okay, the fuel specific gravity is 0.75. Specific gravity is 0.75. So what is the density? Just multiply 1000. It is 750 kg per meter cube. Then the air is initially at 1 bar, and so P ATM it is telling. So P ATM is 1 bar. T is 300 Kelvin. Calculate the throat diameter. Okay, the same question like we solved last. Only the here it is asking different. So I will solve this question. Just solve with me. Calculate the throat diameter for the choke for a flow velocity of 100 meter per second. So it has C2 is equal to 100 meter per second. Velocity coefficient. What is velocity coefficient? We'll see. It is given Cv is equal to 0.8. The pressure drop across the fuel metering orifice is 0.8 of that of choke. So we'll see eventually calculate the orifice diameter. So two diameters we have to calculate. One is throat diameter, one is orifice diameter. So we'll start this question now. So just be very. So see, I don't remember formula, so directly I will put H1 plus C1 square by 2 for first of all for air. Let us calculate for air is equal to H2 plus C2 square by 2. Okay. So C1 is 0. So C2 is a H1 minus H2 into 2 is root over. Okay, now this is 2, same on that derivation. If you remember the formula, then don't need to remember so much, so write so much. So 2 Cp T1, just take Cp outside, T1 outside, so it will be 1 minus T2 by T1 whole root over. So 2 into Cp T1, okay, one minus T2 by T1. Name the, now C2 is given 100. Calculate, T1 is given 300. Cp you know, take it in joule. So it is 1005 joule per kg. 1.005 is taken when it is kilojoule. Okay, calculate what is T2 by T1. Fast. Do the calculation fast. How much you are getting?
I'm doing so.
Calculation you have to do little bit faster. It is somewhat around 0 T2 by T1 is equal to 0.983. So what is P2 by P1 now? P2 by P1 is T2 by T1 to the power gamma by gamma minus 1. So to the power 1.4, 1.4. Are you getting this much? P2 is 0.94.
0.941.
Okay. So P2 we are getting 0.943 bar because P1 is 1. So we get P2 is equal to 0.943. Okay. What will P2 do now? You tell me. Why do we calculated P2? Because m dot A is rho 2 A2 into C2. How to calculate rho 2? Simple, right? This one I already told. P2 rho 2 is equal to rho 1 P2 by P1 to the power 1 by gamma. Do we have rho 1 or not?
Yes, the density,
Density is not.
750.
How much? That is fuel.
750.
This is air. 750 is for fuel. I mentioned. So it is not given. So you have to calculate by P1 by RT1 is P2 by P1 to the power 1 by gamma. Calculate how much you are getting rho 2. P1 is 100. Sorry, P1 is 1 bar. So 1 bar you have to take in Pascal, kilopascal. So 100 divided by 8.314 divided by 300. This is gas constant. So you have to multiply into 29. 1.16 is coming, rho 1. Rho 1 is 1.16. 16 kg per meter cube. This ratio is 1.16. What is P2 by P1? We already have this one, 0.943 to the power 1 by 1.4. You will get rho 2. I'm getting 1.11 kg per meter cube. Okay. So this is 1.11. A2 you don't know. C2 100. It is 5 kg per minute, I think. So you have to convert into second. Are you following it?
Yes, sir.
So calculate A2. 5 by 60 divided by 1.11 divided by 100. A2 you are getting somewhat around 7.507 into 10 to the power minus 4. This is will come in meter square. So now how to calculate D2? 7.507 into 10 to the power minus 4 by pi by 4 whole half. Correct? Are you following?
Yes, sir.
So you will get 0.03092. This one is in meter. So the orifice diameter is 3.09 cm. Somewhat around this one you are getting. Yeah. Okay. Once that is done, orifice is done. Now the jet diameter it is asking. The same thing you have to do. M dot F is equal to rho F, which is given. Area you have to calculate. CF you have to calculate. So CF, what is the formula for CF? This is very easy formula. You should remember 2 into rho F P1 minus P2 minus rho F G Z. This is the formula, right? If you see here, correct? This is the formula.
Yes, sir.
But in that question, the is Z given? Z is not given. What it has said, the pressure drop across the fuel metering orifice is 0.8 that of the choke. So now just try to understand what is the meaning of this. So let us say this is not there. So it is telling P1 minus P2 in the orifice is equal to 0.8 of the pressure drop in the venturi. What is the pressure drop in the venturi? 1 minus how much in air, what was the drop from 1 bar to it dropped to how much? P2 we calculated, right? 0.943. Are you following it? 1 minus 0.943.
Yes.
So how much it is coming? So 1 minus 0.943 into 0.8. It is coming 0.0456. Substitute here. So 2 into 750 into 0.0456 whole root over 750 to 2 root over. You get 8.27 meter per second. Once this is done, calculate AF. 0. I think this is 0.5 it has given. Remember that it is given in minute. Don't forget to convert into second. 0.5 kg per
Okay,
minute.
sir.
So 0.5 into rho f is 750. AF we don't know. CF is 8.27. So 0.5 divided by 60 divided by 750 divided by 8.27. It is coming somewhere around 1.34 into 10 to the power minus 6 meter square. Now calculate df. Divide by pi by 4, then root over. You'll get somewhat around 0.0013 meter square meter. So it is 1.3 mm. Okay,
Okay, sir.
I think yeah. So then we can go ahead. This is the last numerical. Almost same like that. Just I will explain. A 4-cylinder 4-stroke square engine running at 40 revolutions per second has a carburetor venturi with 3 cm. So now we have D2 3 cm. What is a square engine? This one already said, where the stroke is equal to the diameter. Stroke is equal to bore of the cylinder. Stroke is equal to bore. That is called square engine. A 4-cylinder 4-stroke square engine running at 4 revolutions per second has a carburetor venturi with 3 cm throat. Assuming the bore to be 10 cm, volumetric efficiency 75% and the density is 1.15. Of course, density is 1.15 kg per meter cube. Coefficient of airflow CD is 0.75. Calculate the suction at the throat. Means that is, it is asking delta P. You have to calculate delta P. So only the trickiest part is this one. See, what is the volume, the swept volume? How to calculate? Pi by 4 d square L into, this is for 1 cylinder into 4 cylinder. So pi by 4 into d is how much? 10 cm. So 0.1 square into length is also same as diameter, as it is a square. Say engine into 4. So how much you are getting? Somewhat around 0.00314 meter cube. Okay, so we're getting VS as this one. Now, next important, volumetric efficiency. Volumetric efficiency is the actual flow rate of the air when we are considering the flow rate, actual flow rate by the displayed flow of air inside the cylinder into n. This n is the speed of the speed. How to calculate? N by 2 for 4-stroke. So you need to calculate VA. V dot A by VD. VD we have already this one 0.00314 into n by 2. How much is the 400 RPS? So for 40 by 2 is equal to 0.75. Are you following it?
Yes, sir.
No. So V dot A, you will get, this is the actual volume flow rate. So just calculate into 0.75 into 20. So you will get somewhat around 0.047 meter cube per second. Now, as you know the volume flow rate, now calculate mass flow rate. How will you calculate mass flow rate of air? Volume you have, density you have. Density into volume. One point 1.15 into 0.047.
0.054.
0.054. Correct.
54.
I think after this, it is very easy for you to solve because you have flow rate, you have diameter. It is asking suction at the throat. Okay, so it is asking P1 minus P2 for the air. See, one condition, one assumption that I already said, whenever air is considered as incompressible, then you are going to use that formula, that H1 by C1 square by 2, because you cannot use Bernoulli. But as it has not mentioned anything about pressure, so consider it as incompressible. So just calculate P1 by rho F plus C1 square by 2 is equal to P2 by rho F plus C2 square by 2. So it is asking P1 minus P2 is equal to how much it will be? Rho F into C2 square by 2. I think this much. Do you have C? Velocity is given? No, the velocity is not given. Okay, mass flow rate was given, right? So mass flow rate you can calculate. What is mass flow rate of air? From mass flow rate of air, what is the formula? It is rho 2 A2 C2. So 2 into P1 minus P2 by rho F to the power 1/2 is equal to C2. Now just multiply A2, rho 2 and A2, and let us say this thing is 5 into 5 is equal to m dot, we have 0.054. Okay, so can you calculate 5 from here? Because A2 you have, throat is 3 cm, it is writing. Can you calculate?
Yes, sir.
Once you calculate the 5, there from there you can calculate P1 minus P2. Okay,
Okay, sir.
you will get somewhat around 0.041, 0.0451. You can do it. I know, because same type of question we have already solved. Just these are my MCQs. Just tell me, when the throttle is suddenly opened, the mixture from the simple carburetor tends to become what? This one just I told when I was talking about.
Right, sir.
So throttle is suddenly opened. That means what? I told something about inertia. I told. Do you remember? Air
Yes,
inertia is
air would be slower than fuel.
air will be faster than the fuel.
No, not slower.
How? See, whose inertia is more?
But fuel.
Whose inertia is more? Fuel's inertia. So what is inertia? Do you know what is inertia?
Yes.
It means it's a
Yeah.
state body to change its motion. For example, a heavier object is there. Will it the same amount of energy or the same amount of force that is required to move a heavy body is more, or to move a lighter body is more?
I didn't get them.
Sorry.
I didn't get the question.
see, there are two bodies. One is heavier body whose mass is more, and there is one body whose mass is less. Okay, with to whom you have to apply more force so that you can move or you can change the state of motion.
Heavier body, you need to apply more force.
Heavier body. So
Yeah.
so if there is a same suction, so which either air or fuel, which will move faster?
Air.
Correct. So air will move faster. That means fuel will not get mixed properly. There will be more air. Flow rate will be higher of air will be higher than flow rate of. So air fuel mixture will be leaner. Correct? You understood, right?
Yes, sir. Yes, sir.
Yeah. So this is what is happening in oscillation. Okay, then venture in the carburetor results in decrease in air velocity, increase in air velocity. Very simple question. Why there is a venture in a carburetor? Huh?
Increase of air velocity.
Correct. Increase of air velocity, decrease in the pressure, then there will be a pressure difference. The choke is closed when the engine is closed when the engine is
Cold.
Axle.
cold. Correct. Then the lean air mixture is required during idling, starting, accelerating, cruising. Where lean is required? This one already I covered. From this, where lean is there, it is at cruising. Okay. Answer is cruising. Economizer is used to provide enriched mixture during full throttle operation.
Full throttle operation.
Yeah. Then the last question, during the starting petrol engines require what? Stoichiometric mixture, lean mixture, rich mixture, what? During starting the petrol engine.
Stoichiometric mixture.
Starting of petrol engine, what is the, I explained you about idling, right?
Rich mixture.
Yeah, rich mixture. This is only called the idling, right? I explained you so much about idling, what is idle, what is idling, what happens during that. So this is rich mixture. Answer is rich mixture. Okay. I hope you could understand most of the things. I tried my best. I will share all the PPTs and the questions. Go through them. I think with this you will be able to solve your assignment. Most of the questions will be like same, or it will be only little bit different. I think you won't be facing any problem in solving any numerical or any conceptual question if you follow the PPTs, follow the lectures and the questions that I have given. Okay.
Okay, sir.
Yes, sir.
Okay, then I will close this session. Just I am stopping the recording.